Good morning, good afternoon, good evening, good wherever you are, and welcome to this SNIA Cloud Storage Technologies presentation on what's new in container storage. So, if you're at the right presentation, here we go. I'd like to introduce today Keith Hudgins, who works for Dockering. Good morning, Keith. How are you?
Doing good, Alex. It's good to be here.
Excellent. Keith's given a presentation for SNIA before, and I'll put a link in the webcast so that you can see it later on. A previous presentation that Keith did for us at SNIA, which turns out to have been viewed by in excess of 2,500 people. So this is a pretty popular subject. My name is Alex McDonald from NetApp, and I'm going to be your host for the day. So, just a real quick notice about the slides and the presentation. You will be able to get access to a PDF copy of the slides later, and I would encourage you to look at the legal part. There's a couple of things there. First of all, copyright. This presentation is copyright of SNIA, and secondly, there are no warranties with this. If you use the information here, it's very much, I'm afraid, at your own risk. I mean, it's good quality information, but we do have lawyers, and we do like to keep them happy. If you don't know what SNIA do, very quickly, we're a global not-for-profit organization, and we're dedicated to advancing the adoption of storage technology. We do so by using vendor-neutral presentations and material to develop industry and also develop industry-wide standards, for which we enlist the help of subject matter experts. And then we provide, obviously, marketing and promotion materials that aid in the adoption of that. SNIA also provides a range of education materials on storage technology, and if you go to the website, you'll see that we have a huge library to educate the storage community in what is current practice, what is best practice, and some of the interesting new technologies that are up and coming, and to understand implementation and deployment challenges. Most of these materials take the form of white papers or webcasts like this one. And you also will find us at industry events, major industry events, where we regularly have speaking slots. But enough about us, enough about us. I'm going to tell you a little about the CSTI very quickly. We do education, support, and promotion, and attempt to understand the cloud storage technologies. And today's presenter, Keith Hudgins of Docker, is here to help us understand where we are with container technologies. Keith, welcome to the presentation. Yes, and over to you.
Thank you so much. So, real quick, before we get deep into how to connect your storage systems into container frameworks, let's go a little bit of background, just in case people aren't as up to speed on the container world as others, just to give a little bit of level setting. So the fundamental concept of containers is the container itself. And so what a container is it's essentially a single process. It's a self-contained, essentially operating system image, disk image that has one process. And so when the container gets started, the container runtime system will mount the runtime for the container in the host operating system, wall that off and isolate it with C flags and a bunch of other things that keep the container's process in its own little jail. Think of it as a CH root jail, but for the entire process, not just for the file system, and then kick off the process with an init step. The container is not a VM, so it has shared access to system resources, to hardware, network, etc. It'll talk through the host's network system. It'll talk through the host's storage system to reach out to the storage access that it's allowed to talk to. But again, it's controlled. It has controlled access to the system, so containers should not be allowed to reach out and grab anything in the system. The important thing about the container image is that it's a copy on write image that's ephemeral. So when the container launches, the process is reaching out into that image and writes diffs into that image as separate layers. But when the container dies, for whatever reason, whether you shut it down or the process dies or something falls over, that if the ephemeral layers that have been written to that original image are thrown away. So the concept is containers, by and large, live a life from when they start until they stop. That data is not typically retained. That's in the main container image. We'll talk about how that data is retained in just a little bit. And so the ecosystem for containers is is controlled by community organizations. The core technology for containers has been around for a very, very long time. Those of you who've been in the industry for a while will know that we'll have seen this in various and sundry iterations, whether it's Solaris jails, Linux with the LXC project, and even going back to mainframes with various mainframe operating systems. But modern containers are controlled by community organizations. So the technology is kind of run by these two organizations, which are underneath the umbrella of the Linux Foundation. So the Cloud Native Computing Foundation is fundamentally the umbrella project for the Open Container Initiative. CNCF specifications don't specifically apply to containers, but a lot of them do. And then the Open Container Initiative is the umbrella project for all of the projects that descend from that are specifically container-focused projects. And we're going to be talking about a few of those as we go on. And then again, they're all part of Linux Foundation. So after this talk, if you want to get involved in the community organizations and help set standards, these are the organizations to go to, and you can refer back to this slide. So there's three fundamental storage types for containers. First is the ephemeral storage for active processes, which you call the graph driver or graph storage. Then there's cold storage for images. So this is where your container framework will pull images from when you're launching images, and there's ways to maintain that internal into your own environment. And then finally, persistent storage, which is how you keep data safe and available between container restarts as additional volumes. So we're going to start talking about the graph driver, and as we do, we have this this diagram, and we're going to be referring back to this diagram several times. Now, this particular diagram is focused on a Docker Swarm install. This is an older diagram that I used to kind of to just give a brief overview of the conceptual logic of how these things are structured. But a Kubernetes or Mesosphere install looks very similar. So right now we're going to be talking about the active runtime storage, the graph driver. So in this diagram, the green boxes is essentially a host that's running the container runtime, and so in this particular example, it'll be running the Docker engine, and then with a backing store for your persistent storage, volume storage attached, and then inside the system is your graph driver. So that'll be the disk, the disk storage icon that's on the bottom of this diagram. So for the integration of your runtime, of your container runtime images, is basically goes down to two fundamental styles of graph driver. You have overlay or snapshot, and so overlay is uses overlay file system features that are built into the Linux kernel, and those file systems are really heavily limited in which kernels you can deploy them under. So you're not going to be able to run this in the overlay file systems like overlayfs or AUFS. You can't run them in user space. There are no fuse drivers, and you can't run it on older kernels. So if you're in a shop that has a very restricted, that restricts which kernels you can allow in your production systems, you want to look at the snapshotting file systems instead. And the snapshotting file systems are actually becoming the standard as we move forward, and this is true across all container runtimes, whether it's Docker Engine, Cryo, or any of the other ones that we'll talk about in just a little bit. For really good, strong detail on the differences between all these, I've linked a blog post written by one of the Docker engineers in the Moby project, which is an open source upstream project from Docker Engine. I'm not a file system level engineer. I'm fundamentally a Linux system administrator. So when you go really deep on this stuff, I start getting into the weeds. So I would recommend taking a look at that link for deeper information and for some background on why those decisions are being made. So the container runtimes that I was talking about, these are the main container runtimes that container deployments. There's Docker, which is based on Containerd. Docker is the commercial product that my employer makes. Containerd is the open source project that the Docker engine is based on. And then there's CoreOS, which was recently acquired by Red Hat last year, and their fundamental runtime is called Rocket, RKT. The idea of Docker is Docker wants to have control of a bunch of different resources inside itself, where Rocket is a really, really simple kind of Unix-like approach of just the container runtime, and everything else hangs off of that in external services. And then there's Cryo, which is also a Red Hat project. I think it's joint between Red Hat and IBM. I haven't seen a huge amount of updates on Cryo lately, but it's intended to be a Kubernetes native container runtime. All three of these container runtimes are actually projects of the Cloud Native Compute Foundation. So these are meant to work with community standards. They all talk to the same they can all launch the same container images. So if you build a container in a modern container image format, all of these guys are going to be able to launch that container. So just some background for you as we go forward. So we've talked a little bit about the runtime storage. Next, we're going to focus on cold storage of these images. So the cold storage is based on an external service in your container framework that in the Docker world we call Registry Storage. Your local container registry is essentially, if you're familiar with Docker Hub, which is the de facto online resource for container images. Docker runs a really free cost service for anybody who wants to put a container up online. You can search in Docker Hub. You can publish your containers there, and so you don't need a local container storage if you don't require it. However, there's a lot of good benefits on why you might want to. You might want to lock your system down to where only blessed images go into production, and so a local container registry allows you to do that. So there's a bunch of private registry options. There's the open source Docker registry. We have a commercial version, but so does basically everybody else. So all of these container storage systems fundamentally use either file-based or object-based storage to store those container images. So in this case, the container images are stored either as a file, just like any other disk image on disk, or it's stored as a blob in an object store. Docker registry specifically can use either one. I'm not really familiar with a lot of the other ones under the hood, so I can't really speak about how they work, but I know that mostly they use similar mechanisms. You can use any mounted file system in a Docker registry, whether it's direct attached, network attached, or just a spinning disk in the chassis, or you can use the S3, Amazon S3, or OpenStack Swift APIs. We do have some questions coming in. I'll answer questions as we get to the end of the talk because there's a lot of stuff to cover, but I just want to acknowledge that we do have some questions coming in. The final container type or storage type is persistent storage. These are mounted volumes on containers, and that's the box at the very bottom. That's your backing store that's attached to each system. And so basically, as you launch a container, you have the option to mount an additional volume into that container. And where that mount point happens is slightly different between all of your different container runtimes and orchestration systems. With Docker, your orchestration system will manage it down to the container launch, and then it passes it off to the container engine. With Kubernetes, the orchestrator actually manages the mount. So where it happens, it depends on your infrastructure, but fundamentally, what's going to happen is this container gets launched, and during the init process, we'll just bind mount that additional volume into a point on the file system of the container, and we keep on going. So this category is super, super important for most storage vendors. This is where you're going to be able to add value into your customers' container ecosystems as a storage provider, more often than the other two categories. The active images is essentially purely software defined and is mostly maintained inside the container engine. I'm not saying that you can't write a graph driver and integrate that into your storage engine. It is possible, but most people don't care to do that. And then the object storage or volume store or cold image storage is pluggable, but this is going to be where you add a bunch of value. There's not a lot of support in the container ecosystem for native persistence, meaning that right now every one of these systems can essentially map a directory on the disk of the host into a container when you run it. But the problem is that when you're running multiple container hosts, you need that data to be available to basically any node in the cluster, so that when the container launches, the data is available to wherever the container is going to be. And so it's very, very important for third-party vendors to be able to add value to this. So basically, every implementation, I think I covered this one in the last slide, but every implementation basically works the same. The user says, "Hey, I need a volume," and there's a plugin or integration into that container runtime, whether it's a kube driver, a Docker volume driver, or whatever, and then the containers fabric will reach out to that plugin and ask the plugin to provision a volume. The plugin will then provision the volume, bring it back onto the host that the container is about to launch in, mount it, make sure the file system is good, and then it gets bind mounted into the container. The APIs are a touch different, and we're going to talk a little bit about that in just a touch. And some capabilities are available in certain APIs and not in others. We're starting to see some convergence efforts between the various organizations to where the feature parity is across all of the different plugin interfaces, and we'll talk a little bit about that, although that's rather complicated and not really an easy topic to cover in a few minutes. So the fundamental container frameworks that are out there, these are the major container frameworks. You have Docker Swarm, you have Kubernetes, and you have Mesosphere. There are plenty of products that actually that support Kubernetes. Mesosphere and Docker Enterprise both contain Kubernetes support. Kubernetes is kind of the 800-pound gorilla in the market now. And then Docker Swarm is Docker proprietary. Mesosphere is an Apache project, but it has its own commercial offering as well. So the Docker Volume plugin is the first plugin framework that we're going to talk about, and this one I know quite well. mainly because I work for Docker and I've been pretty intimately arranged with the engineering team on rolling this out. There's two fundamental versions of the Docker volume interface. There's V1, which supports both Windows and Linux. And then there's V2, which is much easier for the user to use, but it only works on Linux. The fundamental difference between the two of them, the API is identical. In V2, we containerize the plugin to where you can say Docker plugin install, and it just installs across all of the nodes in your fabric. The problem is with the containerized version is that in order for the container to be able to reach out to the system, we need to have some privileged components, and so we use the Linux kernel capability system to do that, and we can't do that in Windows because that feature or something similar just isn't available in the operating system yet. Microsoft's working on it. But the API is identical. And I've got a link here to the documentation on it. And essentially, what you do here is you create a small web services daemon that binds to either a network socket on each host, and you install this on each host in your cluster. You install it on each host in the cluster, and then edit your config files and for V1 and tell the host what port you're listening on. And V2, we require you to bind to a link local socket just so that we have less sockets hanging around in your network for security reasons. And the plugin control interface does all the reporting back to the host on that. I do say that it requires Docker and Engine, either community or enterprise. That's not 100% true. Mesosphere can also use Docker volume plugins. Mesosphere can use the same APIs. Although the Mesosphere API, if I remember correctly, doesn't work with V2, the V2 spec. Not that you can't run the daemons anyway. But what everybody's mostly interested in these days is Kubernetes. It is becoming the de facto standard. Most container offerings have some flavor of Kubernetes support baked in at this point. There are some growing pains because as Kubernetes is becoming the de facto standard, the community is starting to realize, the user base of the community is starting to realize how complex and complicated Kubernetes is. So in some cases, we're starting to see people look for simpler options, and you're going to start seeing vendors in the orchestration space differentiating themselves on how simple they're making things for the user. I think that won't change things at the storage plugin layer, but it might. So just keep an eye on that. You should definitely be considering Kubernetes integration, and in particular, container storage interface (CSI) integration. That's a strong emerging standard. But be aware, Kubernetes is a community project. There's a lot of cooks. Things change constantly, so you kind of have to pay attention to keep up. So Kubernetes, conceptually, it's very operator-centric. Essentially, if you're launching containers in Kubernetes, the developers who are writing the application specifications for Kube are going to write a control file, which is called a pod file, that describes all the container resources that their application launch is going to have, and then that file gets applied into the fabric, and Kubernetes figures out how to deploy it. In particular, with regards to storage, administrators have to prepare the storage resources, not just plug the systems in and make them available like you would in a Docker volume context, but with Kube you have to do more work. You have to prepare storage classes, which is basically a definition of, it's kind of an SLA definition within Kubernetes, and you can have multiple storage classes point to the same storage system with different rules defined. So as an admin, you define the storage class, and then And then what will happen is the Kubernetes pod definition says, hey, I need a volume from the storage class, and then Kubernetes will create the volume and attach that volume to the Kubernetes pod with a persistent volume claim, which is something that PVC and Kubernetes speak. There's a couple of community links here to get you started on the documentation and how to get involved in the storage side of the Kubernetes project. The Kube storage group is called SIG Storage, and the first link is mainly a link about the group and when they meet online, and the second group is the documentation and how to contribute to the group and how to build drivers and things. So there's a couple of different Kubernetes storage types. The first of these is the entry Kubernetes storage driver. I'm actually going to kind of gloss over this a little bit. Fundamentally, these drivers are shipped with every Kubernetes distro, unless the distribution is actually going into the code and stripping out drivers, which some might do. I know from Docker we don't. In order to contribute to this, in order to add a new entry driver, you have to be a member of the Kubernetes community. You have to sign their contributor agreement. Some employers may not want to sign that contributor agreement and add and volunteer IP to another organization. So that depends on you and your company. This is being deprecated. The CSI is the new hotness, and that's basically what the Kube community is leaning towards by and large. So there's currently an effort to basically not allow any new entry drivers. That being said, the entry driver specification has support for some things that CSI does not currently yet, like snapshots and like you can define how often you want your volume to be snapshotted in a pod if you're using an entry driver that supports snapshots. And the entry driver specification has that support, where CSI is a lot simpler right now and does not have that support. There is some work involved in the Kube community on making sure that there's feature parity between the two plugin formats, so that and in the future, all of the entry drivers are meant to be ported to CSI. But how fast that's going to be, we don't know yet. It's early stages of that consideration. The second plugin type is called FlexVolume. This is the first pluggable API specification that came out for Kube, and there are quite a few vendors who support FlexVolume. It's been fully generally available for over a year now, and the problem is that the docs are kind of hard to find. It's a bit of a second-class project in the Kube storage community right now because of CSI. So the docs are being moved around as they're refining their documentation system as well. So I can put a link to the best location that I could find for FlexVolume docs. It may not be this link may not live very long, so I'm not sure where that's going to be. This is, however, an internal Kube project. It is not being deprecated. It is moving forward. So if you want to build a plugin on a more mature API specification, or if there's particular features in FlexVolume that you might need, then you may want to consider this. For those who are considering doing integrating their storage technology on Windows containers, FlexVolume is basically the only thing you can use right now. CSI doesn't work on Windows. Kube's Windows support is rudimentary right now, but if you want to get into the community with Windows support early, FlexVolume is the only way you can go at the moment. So that's just one thing to consider. CSI is this is basically the new hotness of what everybody's going to in the Kube community, but it's not just the Kube community. There's Cloud Foundry and Mesosphere have announced support for CSI. I don't know what level of support that they currently have. Mesosphere, again, you can also use Docker drivers with Mesosphere, but they're moving that to CSI. because it's a more open community-centered specification where the Docker Volume API is public, but it's controlled by Docker as a commercial entity, and so since CSI is open, they're moving towards that. And a question just came in as FlexVolume persistent storage. Yes, all of these are persistent storage APIs, API plugins that we're talking about in this section. Cloud Foundry, well, Cloud Foundry is not even really it contains container support, but it's not just containers. It's a platform as a service product, so it's not entirely intended for, it's not entirely just containers. And then, so it has its own GitHub project. Its GitHub project is linked here. There's a bunch of useful repositories here, including the actual API specification. So that's all there. So take a look at these links to get involved and to start getting your plugins going. Alex, I think I stepped one slide ahead. We have some time for questions.
We sure do. Thank you, Keith.
Yes, sir.
So let me pose the questions, Keith, because they came in a fairly natural order. And I'll start with, where does LXD and LXC fit into this discussion? That's the Ubuntu or canonical equivalent, isn't it?
Not entirely, no. So LXC is a Linux container specification, and LXC is the old Linux container specification. It's essentially an upgraded version of a chroot jail, and it is a container spec. What LXC doesn't do is it actually works from chroot jail. So you have to build your container environment locally to your system. And it's not as portable as the modern like OCI-based containers. So it's an older container specification that most people are moving towards OCI-based containers at this point. Okay. LXD is just part of the same project. Okay, and
a couple of other questions. How does hardware RAID created volumes play a role in Kubernetes? Does hardware RAID volume need an out-of-tree plugin for Kubernetes persistent volumes?
It doesn't have to be an out-of-tree plugin. There's actually an entry plugin already for iSCSI and for NFS. So it depends on what your hardware RAID system does. So if it's network attached, you can export an NFS share, and then you can use the Kubernetes entry NFS driver if you want to do that. And for direct attached, you can also do iSCSI, depending on how the local administrator and your customers want to do it. Those are really bare bones base drivers. They're not terribly complicated. And if you offer a bunch of advanced features, like if you can create volumes with snapshots and things that that your customers may be interested in, then I would recommend writing your own driver. But otherwise, yeah, you could totally use entry drivers for hardware RAIDs.
Okay, and the last question, I think actually you've got to already. How does the new container storage interface CSI fit in here? I think you answered that quite well in the previous slide.
Yeah, CSI is basically it's the standard that everybody's converging around moving as we go forward. Just to be aware with CSI is that it's a new specification. The spec, the 1.0 spec was just released in December, a month and a half ago, towards the middle of December. So I guess 2 months ago now. So it's brand new. Expected to move fast. And expect just be aware that it's currently a moving target. And one of the other things with CSI is because this is a brand new release, most people do not run Kubernetes by installing open source kube from the internet. Most customers are actually going to install a commercial distribution of kube to make it easier and to have support. The commercial distros tend to lag behind the open source releases by a few months. Case in point with Docker. Docker does not officially support CSI right now. The version of Kubernetes that we ship with the current release of Docker is 1.11. The current kube release is 1.13, and 1.13 is the version that went where CSI went GA. And in fact, 1.14 is about to be released, and so we're going to be a couple of versions behind until our next commercial release in a few months. So, so just be aware that the commercial support for some of this stuff lags behind the open source releases, just because it takes us time to get it all integrated and QA'd through our release process. And this is true for everybody.
Okay, thank you. Okay, so I'm about to put up a notice. That's the link to the presentation today. Now, the link actually contains a few other bits and pieces that we didn't put into the slides originally, but we've added. And firstly, Keith's other presentation on Docker is there, along with a couple of other presentations we've done on containers and persistent storage. One of the other things we're going to be doing, or two in fact, because we're going to do a pair of them, we're going to do a Kubernetes in the cloud presentation on April the 17th, which will be a relatively high-level introduction of what Kubernetes is about, use cases, etc. And then we're going to follow that up shortly afterwards with another Kubernetes presentation where we're going to get into a bit more detail. So there's quite a lot of interest in this area in terms of Docker, Kubernetes, Mesosphere. There's a huge amount of work going on at the moment. The ask I have of you as we leave this presentation today. First of all, thank you very much, Keith, for the presentation. So if you could rate this webcast and provide us with feedback as you leave. I've pasted up the presentation link so you get a copy of the slides. Remember to read the first couple of slides that contain what you can do with them, you know, the restrictions in terms of the copyright. But use the links in the slides to get full access to everything that Keith's talked about today. And we're going to post a Q&A. All the questions that have been asked, we'll post up answers on our website. We've had one extra question in from the audience, which I'm actually going to take because it's actually quite an interesting one and pretty dear to my heart as well. Are there plans for Docker support for persistent memory, new class of memory? Keith, are you aware of anything?
There's no current plans that I'm aware of. It's something that I know we're keeping an eye on, but it's new enough that we've got a bunch of other stuff that's higher up on our priority list at the moment. So we're gonna. I think the intention is to wait for the community to kind of center around on technology, on like technology standards for it, and for it to become a bit more commercially available before we work too much into it.
Okay.
It's definitely something we're considering.
Yeah, persistent memories. I'm really interested in persistent memory at the moment. It's one of the big differences in technology that we've had. If you thought SSD was fast, wait until you see persistent memory. Anyway, that's a completely different topic. We've got loads of presentations on that too on the SNIA website at snia.org. Thank you very much, Keith. Thank you very much to our audience. Thank you for attending today, and we look forward to presenting you with new and interesting topics. That April the 17th presentation on Kubernetes will be the next presentation of the Cloud Storage Technology Initiative. Thank you very much indeed, and have a great day.
Take care, everybody.